Hi all, welcome to part 9 of the video lecture on counters. So part 8 onwards we started discussion on synchronous counter, and in that we saw a basic idea about this sequential circuit, in particularly that synchronous sequential circuit in general, and what is that excitation table, characteristic table, those things we observed, and we need them for understanding the concept we are going to see here. So here let's start with the something called a 3-bit binary counter, and we already see already saw how to implement this 3-bit binary counter in an asynchronous manner. Binary up, by default binary counter means binary up counter, so its state diagram is familiar too, right? So we will start with this 0, and then we will go like then 0, then 1, then 2, 3, 4, 5, 6, 7, and back to 0. So this is a up counter. Similarly down counter also, all those things we already designed using asynchronous circuit. Now here we will discuss how to design this using a synchronous sequential circuit, okay, in a synchronous way. Yeah, so the idea I will just tell you, like so here I am having 3 bits, right? So let me denote the bits like A2, A1, A0. So I am observing all the possibility for this A2, A1 and A0 at any point of time, right? So at any point of time, if I am observing these bits, say what I'm simply observing this A2, A1 and A0 currently. So it can be in any of this state, like it can be in this state, or it can be in this state, or right. These 8 possibilities are there. I don't know at what possibility is there at any moment, right? Now after applying one clock cycle, so this is a current output, right? After applying one clock cycle, so how this state is getting changed, okay? So new state, the present state and next state, like that you can write, or if you want you can denote it using something different. If you sometimes in some textbook, this is denoted by A of t, and this is denoted by A t of t plus 1, so that it is clear after one clock cycle this is the output. Similarly, this can be denoted by A1 of t, and this can be denoted by A0 of t, and correspondingly these things you can denote by A1 of t plus 1 and A0 of t plus 1. So it's up to you, either you denote like this, or you mark this as the present state, and this as the next state, okay? So anyway, it's getting complex. Okay, so this way you can write. So what I was trying to say is, so this is the thing. So hope it is clear. Now if I am at the current clock cycle, so after getting on clock cycle, this transition is happening, right? Either if it is positive edge triggered, after that positive rising edge of the clock, it will transform to 0, 0, 0, it will transform to 0, 0, 1. Similarly, if it is currently, if it is at 0, 0, 1, after applying on clock cycle, what is the next state I want? I want it to be in 0, 1, 0. Similarly, from here I want it to be in this. Here I want it to be in 4, right? So from 4 it will just move. If the current state is 4, it will change it to 5, then 6, then 7. And finally, if it currently if I am in 1, 1, 1, 1, after applying on clock cycle, I will go back to 0, 0, 0. So this is a kind of state transition I am in need. The same this is, if this is your state table, state diagram, this is your state table. Same diagram I expressed like a table, okay? So that transition I expressed. Now with the help of the state table, you can see what are all the inputs to the flip-flop, and we can implement this particular counter, up counter, say using JK flip-flop, SR, and not SR because the toggling is needed, okay? JK flip-flop, D flip-flop, or T flip-flop, all are possible, but mostly by default in the question, if nothing is mentioned, just they are asking you to implement this up counter, it's better to use T flip-flop, because T flip-flop, it is very easy to implement. Only a single input you have to take care. Otherwise JK for the first bit transition, like how A2 is changed to A2 T plus 1, right? A2 that transition will be controlled by one flip-flop. So similarly so as it is a 3-bit counter, we need three flip-flops are needed, right? So 3-bit counter, we need 3 flip-flops. And what kind of flip-flop you can use? It's better to use the T flip-flop. That is my request, because I will tell you otherwise what will happen. It will be difficult. More equations you have to minimize and all. it will be time consuming, right? So if it is T flip flop, so I am having T input to all of them. The output of this one I am calling as A2, or yeah, that you can take in any order. Anyways, how they are implemented, that is what I'm looking. Okay, anyway, in the reverse order it's that also fine. So here they are taking like that, A2, and here let me denote it as A1, and its output be A0. Okay, so that is something I'm getting. And what about the clock? Here the clock is something fixer, like to every flip flop I am applying the common clock. Okay, so the common clock is being applied to all. Fine. Now this is clock. Now what about the T input? That is a question. What about the T input? In a synchronous circuit, the T input was like one asynchronous circuit. Hope you remember. But in synchronous circuit, it is not like that, because clock is something differently given, right? So accordingly, some change will be there. So the main task is for you to find out what is this T. So let me denote. So this let it be flip flop 2. Okay, so let it be flip flop 1, which is giving this A1. Let it be flip flop 0. So let it be T0. This is be T1, and this is by T2. Okay, or they are denoting like the T input corresponding to A0 in that way. So the notation only you can either write like this, or these inputs, you know. What is T input for this one, what is T input for this one, and what is T input for this one. So that is what you have to find out, right? So you have to find out what is this TA2, and similarly what is this TA1. So that is your task. And then the circuit is complete. The other things we know, because clock you have to apply commonly, and from A to A1 A0 you will get the counting, right? And the input only you have to decide. So that is a task here. So now the first flip flop is actually giving a transition for A2. So initially we can assume that they are all in the initial state, that is 0. Now from the 0, after applying one clock pulse, it should change to 0 0 1. I mean, for this bit not change, this bit not change, then this bit there is a change to 1. So that is a requirement I need, right? So accordingly I have to find out what is this TA2, and what is TA1, and what is TA0. Okay, now tell me the A2 bit, right? A2 bit, if it is 0, I want to retain it as 0. So for retaining 0 as 0, the toggle flip flop, the input should be 0, right? So whenever I am giving this as 0, this 0 will be retained as 0. Similarly here also you apply 0, so that this also will be retained as 0. Fine. But for this one you have to apply 1. And that one will change, toggle this to 1, right? So here you have to apply. So is that idea clear? So what I was trying to write there, let me remove it, otherwise it will confuse at some later point. So this 0 is to be changed to 0, so that I don't want any change. I want to retain that information. That is, so I have to apply the input as 0, and the least significant bit I want to change from 0 to 1. I mean, the last flip flop should be in toggle mode, so that its input should be 1. Is that idea clear? Now similarly, what about this? From 0 0 1 I want to change to 0 1 0. For that, A2 not change, A1 should be toggled, so that you have to apply the toggle input. A0 also should be toggled. Fine. Similarly here, 0 to 0 not change, 1 to 1 not change, 0 to 1 toggle. Fine. Similarly here, I am reading like this, 0 to 1, then like that I am filling the table. Okay, so hope that is clear. 0 to 1 I want toggle, 1 to 0 I want toggle, 1 to 0 again I want toggle. 1 to 1 no change, 0 to 0 no change, 0 to 1 toggle, 1 to 1 no change, 0 to 1 toggle, 1 to 0 toggle, 1 to 1 no change, 1 to 1 no change, 0 to 1 toggle. Again here all bits are to be toggled, right? So that about it. So this is how you have to give. So that's all. So in all possibility, at any point of time, if you are applying TA2 like this, you will achieve that corresponding transition. And we explored all possible transitions also. Now tell me what is your TA2. Now your TA2 will be something like you can denote it like you can express it as a function of the present state. What is the present state? A2, A1 and A0. I mean this one. or a2 of t, okay, the present state as a function of the present input, you can express it. Now how to find out it? You have to use a k-map. Okay, I will just tell you this ta2 alone. Let's see the expression. With the space available, I am drawing here the k-map for ta2. Okay, let's see that. There will be 8 cells, and the inputs are like a2, a1, a0. Combinations are like 0, 0, 0, 1, 1, 0, 1, 1, and here it is 0, 1. The possibilities are like 0, 1, then 2, 3, 4, 5, 6, 7. So these things are like this corresponds to 0. So now the inputs are like so you just have to focus on this one only, and the min terms corresponding to this is min term 0, 1, 2, 3, 4, 5, 6, 7, and you can see that this min term 3 is 1 and min term 7 is 1. Only these two things are 1, 3 and 7, right? As these two are 1, so you can group them like this, so that the corresponding term will be a1, a0. Okay, so I obtained this ta2 as a1, a0. Similarly, you have to find out what is your ta1 and ta0. Now you got the idea, right? So all of you try it yourself. And anyway, I just given the solution also. So this is a table I explained in the previous slide, right? The state table of a 3-bit counter, and this is how you can. So this is what we see now, right? The truth table, the k-map simplification for ta2. Okay. So this is something I discussed. Similarly, you try for this, you will see that this ta1 is getting 1 for 4 cases. The last one, all are 1. So I don't know whether you noticed or not. In a k-map, if all bits are 1, means the input is just 1, right? So it's always 1. That is the meaning. So whatever be a2, a1, a0, this should be 1. So that is the meaning. So there are other interpretations also. We may see that in the next video. So what about now? Tell me how to implement this. Finally, we are having the 3, as it is 3-bit counter, we are having 3 t flip flop, right? And for t flip flop, we applied that common clock. So common clock is applied now. And after that, we are observing what is the t input for the least significant bit. For least significant bit, we got the ta0 as 1. So this is 1. And now can you tell me what is the meaning of this? This least significant bit is 1, means the last flip flop should be in toggle mode. It will always toggles. Okay, so that is the meaning of this one. Now what about the t input of the second one? ta1. So this is what we denoted as ta0, and this was our ta1. Similarly, this was our ta2, and we saw that ta1 is nothing but a0. So this a0 you take and apply. So this is nothing but so you are taking like this, right? This is your a0. And similarly, what is ta2? ta2 is AND of a1 and a0. So from here you are getting a1, and from here you are getting a0, and here you are getting a1 dot a0, and that is your ta2. So this is how you implemented the circuit. Now the question is, can you see something interesting here? So can you generalize it for a 4-bit binary counter, or some if I am doing this way, the state table kind of realization, it is fine, but here just a 3-bit counter, we are having a state table with 8 entry. Now for a 4-bit counter, the state table will be containing some 16 entry. Okay, fine, we can try that also. Now for 5-bit, it will be 32 entry, so it will be tedious from that point onwards. Also you have to use a 5-variable k-map. Okay, so that will be tricky and difficult, right? And for 6-variable, it is more tedious, and we don't even study that 6-variable k-map and all. Okay, so try to come up with something different. Okay, so if I am asking you a 5-bit counter or 6-bit counter, you should be able to implement. So here I am talking about an up counter only, a 5-bit up counter, or by default binary counter means up counter only. So can you observe something beyond this? Okay, so this is the implementation we got or something like this equations we got, just think about it, right? So can I come up with a generalization for this? So 4-bit or 5-bit, can I have the design in a easy way, tricky way, without going through this tedious method of characteristic table and k-map minimization and other things? Okay, so that we will see in the next video. Yes, thank you.